So today what we are going to do is to look at the basics of what an architecture can look like, a hardware architecture for solving a given problem, right? For us, an example DSP problem, right? We'll take a very simple example, come up with a very basic architecture for it, and from there sort of see how we can modify it to make it incrementally sort of programmable and eventually sort of get the idea of how a general architecture is likely to look, okay, and that will sort of give us a flavor of both how programmable architectures look as well as how we can build custom architectures for solving problems that are not limited to solving just one problem but might have some extensibility in some ways, okay. So the example that we are going to look at is the so-called FIR filter, right, which is essentially defined by the equation y of n equals, I am going to take a very specific example of an FIR filter, a very trivial example. It has three coefficients, a times x of n plus b times x of n minus 1 plus c times x of n minus 2, okay. A, B, C are some constants, some coefficients that have been defined based on some characteristics that we require the filter to have. X of n is the input, okay. So therefore x of n minus 1 is one previous sample of the input, x of n minus 2 is two samples previous, etc., right. How the numbers are represented, how many bits are used, etc., I am going to ignore for now. We will get into that in probably the next one of the next two classes, right. Number representations and so on we will spend some time on, but for the time being I am just going to assume that we know how to represent these values in some binary format, and things like multiplication, addition, etc. are known. We know how to do those operations, okay. So if I asked you to just outright, build a hardware architecture that implements this, what are the things that you are likely to require and how would you go about building it? A shift register, right, probably is the most sensible or the most obvious way to obtain x of n minus 1 and x of n minus 2 from x of n, okay. So what would that look like? It would essentially say, fine, my x of n is coming in here, right, and this arrow over here essentially indicates it is some kind of a multi-bit bus. It could be a 16-bit bus, something like that. All that it means is all of those data are synchronized, they are changing in sync with each other, okay. The shift register essentially says there will be some block which I am going to just use a rectangle to represent, and at the output of that block is going to be x of n minus 1, right. The implicit assumption over here is that I have some kind of a signal which is basically the sample clock which is going to come to this register, okay. I am not going to draw the clock from now onwards. I am just going to assume that whenever I draw a rectangle like this, it is understood to be a shift register, okay. There is another shift register because I also need x of n minus 2, right. Of course it has the same clock, otherwise it would not really make sense to use a register like that, okay. Alright, so far so good. I have got x of n coming in from somewhere, and from that I am deriving x of n minus 1 and x of n minus 2. What do I need to do with all of these values? Multiply by the corresponding coefficients, okay. Alright, so let's see how we'll do that. I'm just going to draw it as a block that says A over here, another block that says B, and a third block that says C, right. So what I mean by this is that x over there indicates that it's a multiplier, and the value next to it, A, B or C, indicates the coefficient that's being used to multiply. Now I need to add all of these together. Rather than just pulling all of them into a single adder, I am going to assume further that my adders themselves are two input adders, okay. Therefore one way of doing it is to have one adder over here and say I'll take this and add them together, this and add these two together, and as a result I get y of n out here, okay. So hopefully it is obvious to all of you by now that this is not a unique architecture, right. There are other ways in which I could have made these connections, right. So for example, why did I choose to add the A and B multiplier outputs together first and then add them to the C multiplier output? Could it have been done by having one single 3-input adder, right? Could I have changed the direction of some of these signals, done it in a different order, some other way of doing this? All of that, in other words, there are multiple possibilities, okay? And this is just one example. Of course, it is a reasonably obvious example, obvious architecture that we can come up with. So it's hard to really find fault with this. Okay, so now what can we infer from this architecture? Once I have come up with this architecture, the questions that I need to ask are essentially, one question that I would want to ask is, how fast can this process data? Okay, and what determines that? What would it be that determines the rate at which this architecture can process data? Assuming that somehow I can provide my input samples fast enough, right? Remember, we had this discussion earlier where we said that normal signal processing algorithms have this property that very often their sampling rates are set by some physical constraints. Some property such as, for example, there's no point in sampling voice at more than, let's say, 44 kilohertz or something like that, even music, right? Because the human ear cannot really sense anything beyond that. Similarly, for vision, more than 60 frames per second is unnecessary because you really can't make out that level of detail. In fact, 30 frames per second is the limit of persistence of vision, right? So there are physical reasons why certain signal processing applications have a required sampling rate, okay? But in this case, I'm going to leave all that out of the picture and say, from my architecture side, what limits my performance? Okay, how fast can this run? How fast can I sample and process data when I operate with something like this? What would it be that is my limiting factor over here? The clock period, okay? So in other words, as I've shown over here, essentially the clock that I have over here, this is both the clock period and that happens to be equal to the sample period, right? Why am I saying that? Because my assumption is that by connecting the clock like this to the registers, right, I am essentially saying that every time there is a positive edge of the clock, a clock tick, one sample gets transferred from input to output, okay? So every time there is a clock tick, there is a shift of one sample, therefore the clock period and the sample period in this case are the same, okay? So then asking what is the highest rate at which this can sample is the same as asking what is the highest clock period, or rather the highest clock frequency that can be used with this circuit. And what determines that clock frequency? The critical path through this circuit, right? The critical path essentially being the longest set of combinational elements that is present in this circuit, which effectively, if you look at it, comes down to this path over here, okay? Because there is an implicit assumption that there is some kind of a register at the input side over here and also a register at the output side. Those have not drawn, but those are implicit, okay? So if I take those two into account, this becomes the critical path, right, which determines the minimum time period, or in other words, the maximum frequency at which this system can operate, okay? And in this case, supposing the delay through a multiplier, let's call it Tm, it would probably be some, either 1 nanosecond, a fraction of a nanosecond, or 2 nanoseconds, some number like that in units of time, okay, some number of nanoseconds, hopefully. But then there are also two adders, right? So Tm plus 2Ta seems to be the critical path through this circuit, okay? So implicitly what I am assuming over here is that I can associate one number, right, called the delay through the multiplier or the delay through the adder, and say this is the propagation delay through an adder. Now in practice, what you will actually find is the actual delay through an adder depends also on what inputs are actually given to it, because if there is a pair of inputs that causes a long ripple through the carry chain, the actual delay before the outputs settle down to their final values will be higher than if I am just adding, let's say, 0 plus 0, where nothing is changing, right? Or even 0 plus 1, where maybe 1 bit changes at the output, okay? So the Tm and Ta, in other words, are typically assumed to be the worst case delays through the units, because ultimately critical path we are interested in worst case performance. So Tm plus 2Ta is the critical path through this circuit. So what kinds of hardware elements are we using over here? We are essentially saying we have multi-bit shift registers, right? Why am I saying multi-bit? Because all the bits corresponding to x of n have to be synchronized and loaded into that register at one time instant essentially, okay. The enable signal or whatever it is that I use in order to load data into the register has to be one synchronized thing across 16 bits, so that all the 16 bits of x get stored at the same time instant. I have multipliers. How many bits are these going to be? That depends on my number representation. We'll look at all that later. And I have adders. Okay. So as long as I have some way by which I can design adders, multipliers and shift registers, right, or registers, and I can just connect them up, I can get this hardware architecture built. I can actually probably even put it together on a breadboard if necessary, or I can do a custom layout and get a IC chip designed out of this. Okay, not very hard to do. Okay, so far so good. What are the drawbacks with this architecture? What problems can you think of with this architecture? If I have the values of A, B and C hard coded into the multiplier, it simply means that I cannot change them. On the other hand, if I had something where, let's say, I have the same architecture, but somehow I say that this is going to get its input from some other register, this is going to get its input from yet another register, and this is going to get its input from a third register, and I store the values of A, B and C over here. Okay. Now to some extent at least that can be changed, right? I have made my architecture slightly more complicated, and my multipliers are now no longer specialized. They are actually general multipliers that can multiply any coefficient with any input value, okay, because I could change the values of A, B and C while the system is operational, okay. Then of course it raises the question of how am I actually going to load values into these registers, right? There can be some load enable, there are ways by which it can be done, but it also increases the complexity, but at the same time, it's not very easy to do, okay. So that's one part of it. At least if I want to change the coefficients, I could handle it that way, right? What about the next question? What if I want to change the number of taps? Instead of having 3 coefficients A, B and C, I want 4, A, B, C, D. What would I need to do? I pretty much have to redo the design. I mean, it's easy to draw what is needed, but in terms of the hardware, I have to resynthesize. Okay, there's really nothing else that I can do over here. Okay, so that's yet another drawback. So if I try listing the drawbacks, one is changing coefficients is not easy. Changing number of taps requires recompilation essentially, or resynthesis. And the other one is the clock and sample, these being tied together is not necessarily a good thing. It basically means that yes, I am designing a system where even if my sample period that I require is only 1 microsecond or few milliseconds, I basically have to create, and and my clock in principle could operate at, let's say, a few megahertz or even gigahertz. It doesn't matter as far as I am concerned. I still need to just operate that system at a slower rate, right? My registers that are capable of switching at hundreds of megahertz are going to be kept slowly switching at whatever rate that is actually required by this clock, okay. So even the fact that my hardware may be capable of operating much faster than I need, I can't really make use of that, okay. Is that necessarily a drawback? In some ways, yes, for the simple reason that maybe I could have come up with another architecture that did not need 3 multipliers, 2 adders, in order to implement this operation.